Hi students, in this first video for chapter 6, we are now going to talk about the covalent bond and building Lewis structures. So what is the covalent bond? A covalent bond is a chemical bond in which two or more electrons are being shared by two atoms. In our previous chapter, we talked about the ionic bond in which electrons were being moved to another atom so that we could form an electrostatic charge. In this case, the covalent bond is going to keep the electrons with the atom, but now we're going to put them in between two bonding atoms so that they can share them. So why should two electrons be shared between two atoms? Let us go ahead and look at our fluorine. Notice that it has 7 valence electrons. Let us go and bind that to another fluorine that has 7 valence electrons. Using the ionic model, we would have to give up an electron from one of these fluorines to give it to the other and build a charge difference, creating a positively charged fluorine and a negatively charged fluorine. But fluorine does not want to be positively charged. So what is better in this case is going and sharing a pair of electrons between the two atoms. Notice that the two electrons being shared between the two atoms are shown as dots in between the two atoms. So seeing that we had 7 electrons with one fluorine and 7 in another, we are able to now get what is known as our octet. We like to have 8 valence electrons around one of my fluorine as well as the other fluorine. Just consider this like a Venn diagram where the 2 electrons that are being shared by the Venn diagram are actually being double counted by both atoms. Those electrons are temporarily between those two, helping with our electrostatic abilities and being able to create some stability. So the Lewis structure for this is very, very important. We are going to draw dots differently. We historically would like to show our lone pairs as dots. This is going to be incredibly important when you get to organic chemistry because those dots will then represent other reactions that this molecule is able to do. However, a covalent bond is going to take the dots in between our two atoms and symbolize them as a line. This is one of the major differences that you must be able to denote. Dots are used for lone pairs, while lines are used for bonds. I do not want you to be using lines for your lone pairs because that should be used to show that there's an interaction between two atoms. So lone pairs are dots, then our bonds are going to be our lines. So what can we do and how do we form all of these various different structures? Well, let's start off with the Lewis structure of water. Notice that I have a hydrogen with 1 valence electron. Then I'm going to have an oxygen with 6 valence electrons. You will notice that it has 2 vacancies that we would like to fill. And then finally, we can go and add in a second hydrogen, the third atom of our water. And notice that we are now going to get a stable molecule for all of our atoms. The most important thing in here is that the oxygen is going to get its octet. This means that it has its 8 valence electrons. Yes, 2 of those are being shared from the hydrogen, but inside of its bonding orbitals, we are going to have a stable octet. The other thing you should notice is that hydrogen only prefers to have 2 valence electrons. This is because we want to populate the 1s orbital, so we are only going to use 2 valence electrons when dealing with hydrogen. You can see that the other hydrogen has 2 valence electrons, and as you'll notice with our shared pairs for our Lewis structure, you are going to see that we have changed those bonding pairs of electrons to lines. We will call those single covalent bonds. We will call those covalent bonds. We'll call those nonpolar bonds. We will call those many different vernaculars along the way, but in many cases, it's just best to call it a covalent bond because it may not always be polar or nonpolar, as we've seen with the differences in electronegativities. Now we've got to show how to form multiple bonds. This is when 2 atoms will share 2 pairs of electrons, meaning a total of 4 electrons. This is carbon dioxide. Our carbon dioxide actually has this Lewis structure. So how does this work? Well, notice that my left oxygen has 8 valence electrons. This is coming from 2 lone pairs, those electrons specifically on the oxygen and the property of the oxygen, and then 2 pairs of electrons that are being shared with my carbon. If I look at my other oxygen, you will see that it has 8 valence electrons for its octet. And the nice part here is that carbon is going to be sharing all of its pairs of electrons with its neighboring oxygen atoms. So carbon in this case has no lone pairs. If we go and draw this with our representation, each one of these pairs of electrons is going to be symbolized with a line. You can see that here by drawing our double bond. Our double bond looks like a double line stacked vertically attaching the atoms that have the electrons. Yes, we can go to double bonds, but triple bonds is actually typically as far as we can go. These are 2 atoms that are going to share 3 pairs of electrons or 6 total valence electrons. A great example of this is our molecular nitrogen. Notice that nitrogen would be bringing 5 valence electrons for each atom, but then what is going to happen is that we are going to see 8 valence electrons in one nitrogen's octet, 1 coming from a lone pair and 3 shared pairs. And as you can see with the other nitrogen, we will have the same analogous set of 3 shared pairs and 1 lone pair. Those shared pairs will now bring a triple bond, which is symbolized by 3 vertical lines between the 2 atoms. So as you can see here, lines are incredibly important because they will tell you the bond order and how many pairs of electrons are being shared. Lone pairs are important because they are symbolized by dots, which will allow you to show what other further reactions or how much electron density is around that atom. So now I'm going to give you the rules for writing Lewis structures. The first one is that you must draw a skeletal structure. This is typically the bare minimum of electrons used to go and bind a molecule together. This means that we are going to use 1 pair of electrons between each attached atoms. You want to put the least electronegative atom historically in the center. If it is not, I would give you some reason as to why it's not, or tell you what the central atom is. Rule 2 can be historically the most difficult part of this process. That is counting the total number of valence electrons. This means that we are going to look at what column our element is in, and we are going to use that as the number of valence electrons. So in the case of the noble gases, it would be 8. In the case of the halogens, it would be 7. If we go to the oxygen group, that would be 6. The nitrogen group would have 5. Carbon group would have 4. We are going to work on this and make sure that we have the right number of electrons. Another thing we have to do is look out for charge species. If we have a negative charge, we must add 1 electron. So if we were to have carbonate, CO3 1-, we would need to add 1 electron to the total electron count. If we have a positive charge, like that of ammonium, we would need to subtract 1 electron because we need to have a positive charge. Then what we are going to do is complete the octet for all atoms except for hydrogen. Remember that hydrogen would prefer to have 2. The octet rule is a very nice guide, but as we work through this chapter, you're going to see that it is just merely an outline, and that stability will come later with a different term. Historically, when we are filling the octet, we want to start with the outermost atoms first. So this is because they are typically the most electronegative. So as we complete the octet, we want to start with the outermost atoms first. Then what will happen is that we will be able to place extra lone pairs on our central atoms, or if in the case we have too many electrons, we are going to be able to form double bonds and triple bonds on the central atom using the lone pairs from our outside or terminal atoms, and this is going to be able to give us our best structure. Once we are done with these rules, we want to be able to look at them and make sure that all atoms are satisfied electronically. But let's look at a few compounds that are actually going to violate our rules. The first one is an incomplete octet. Let us go to beryllium hydride. First off, we have a total of 4 electrons. How can we get to 8 if we only have 4? This is where you must be very careful not to add electrons you don't have. So in this case of beryllium hydride, you will notice that I will use the total of 4 electrons to bind the beryllium to the hydrogens, and that beryllium is going to have an electron deficient stability. This means that it is actually stable without having the octet. So notice that I will have my 2 bonding pairs, but I will have no lone pairs to my beryllium. The next one we want to look at is boron trifluoride. Notice that I will have 24 total electrons. And if I go and draw the Lewis structure, notice that I'm going to have my 3 shared pairs holding the fluorines and the boron together, but using the rule in which we add electrons to our fluorines first, because them being the most electronegative, the boron does not have a lone pair. This is a case in which many students will go and add a double bond between the fluorine and a boron, trying to give boron a complete octet. But as we will show you later when we start discussing formal charge, this is actually going to destabilize our molecule. So right now, as you see it here, this is going to be a much more stable molecule. So as you can see here, I've used my 24 total electrons. My boron will only have 6 electrons in its valence orbitals. As you can see here, this is what the molecule looks like. We will work on our shapes when we get to our molecular geometry chapter. So what happens if we had odd electrons? Well, if we go to arguably the most angry of our atoms, notice that it just says no. If I do an electron count, I end up with 11 electrons. This means that I will get this Lewis structure. I cannot get 8 electrons for my nitrogen if I have an odd number. But the interesting part about this is that this is incredibly stable, and we will discuss this when we get to our formal charge rules. So because we have an odd electron count, this means that we will not get an octet. Many compounds will try and run into this situation, but then they will add a charge or a positive charge or a negative charge in order to try and get the stable octet for each atom. Finally, the last group that does not follow by the octet rule is what we call expanded octet, and this is when a central atom, typically with a principal quantum number greater than 2, so where you're looking at row 3 atoms and below, we are going to be able to add more electrons around the central atom. So let us go ahead and look at sulfur hexafluoride. This is going to have 48 total electrons, and we need each fluorine to attach to the sulfur. That can be done here. So as you can see, our sulfur has a total of 6 bound shared pairs, each one to the fluorine, and then our fluorines are going to have each one of their octet, with each having 3 lone pairs. This is incredibly stable. This will also give us a different molecular geometry, and we'll use different orbitals, and we will discuss that in a further chapter. But the nice part about this is that it will use our total electrons. So if you see that we need to have more than 4 attachments, say 5 or 6, you're more than likely going to see an expanded octet exception to our rule. So notice that our sulfur has 6 bound pairs and can be considered expanded octet. The fluorines, however, still abide by the octet rule. So let us go and try some various examples on how to draw Lewis structures. So it says, write the Lewis structure for nitrogen trifluoride in which all 3 fluorine atoms are bound to the nitrogen. So the first thing that I need to do is go and do my skeletal structure. So that means that I must have fluorine bound to nitrogen, which is bound to the other fluorine, and finally to one more fluorine here. So I have my skeletal structure. The next thing I need to do is my electron count. For my nitrogen, I am going to get 5 electrons, and for my fluorine, I am going to get 7 each. So that is 21 plus 5 is a total of 26 electrons. As you can see, I've already used 6 of them, 2 with each of my 3 shared pairs. So that means that I have 20 electrons left that I must add. So I will start with the fluorine. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. I have 2 more. Our nitrogen is deficient, and to make it have an octet, I can go and add a pair of electrons on my nitrogen. So as you can see with my nitrogen, I have 3 shared pairs and 1 lone pair. This is going to be the correct Lewis structure. Let's go ahead and try the carbonate ion. We have used this previously when we were discussing some of our ionic compounds. So the first thing that we want to do is go and build our skeletal structure. So there is an oxygen bound to a carbon. There's my other oxygen, and finally my third oxygen. So now what I need to do is go and look at my total electron count. Carbon will bring 4, and each of my oxygens will bring 6. So 6 times 3 is 18, plus 4 is 22, but now we must also be concerned about this -2 charge. Remember that this is going to give me 2 more electrons. So in this case, I have a total of 24 electrons to use. I have already used 6. So now if I subtract the 6 electrons from my skeletal structure, I have a total of 18 electrons to go and use. So we go and put them on the most electronegative atom first, which in this case will be my oxygens. So as you'll see here, I'm adding all of my lone pairs here to my oxygens. And you will see that after I've added the lone pairs, I'm out of electrons. I've used all 18. But my carbon is electron deficient. This means that I must go and use 1 pair of electrons and go and form a multiple bond. I will choose to use this pair of electrons and go and put it here. This means that I would end up getting my upper left oxygen to be doubly bound to my carbon. There is my right oxygen with its lone pairs. And finally, here is my bottom oxygen. And this is a good Lewis structure. Now, this molecule is not totally complete. If it is charged, it is best for us to put it in brackets and signify that this is going to have a 2- charge. We want to signify that we have added those 2 electrons in to create this stable ion. Another further question is that you notice that I added the double bond to my left oxygen. Could I have done it from my right oxygen or maybe the bottom oxygen? If I'm able to do equivalent electron moves to get similar structures, we call those resonance structures, and we will deal with those in a future video in this chapter. Finally, let's go ahead and look at our aluminum triiodide. So in this case, we need to go and build our skeletal structure. There's my iodine. Our aluminum is in the middle because of it being the least electronegative. And finally, we can put our last iodine there. So now, how many total valence electrons do I have? Well, aluminum is bringing 3. Each one of my iodines is going to bring 7. So that is a total of 24 electrons. I have already used 6 of them in my skeletal structure, so I now need to go and place 18 more electrons. They go around the most electronegative atoms, which are in this case the iodine, so I will put those in now. And you will notice that when I am finished with the lone pair on the iodine, I have run out of electrons. Many of you are going to try and form a double bond, but this is actually a electron deficient molecule. This is stable as is. Aluminum would prefer to have only 3 bound electron pairs. We are not going to try and make a double bond on any of these species. We will talk about why this is the case when we get to formal charge later in this chapter. So finally, let us go and do this example. Draw the Lewis structure for phosphorus pentafluoride, PF5, in which all 5 atoms are bound to our phosphorus. So if we do that, we have our phosphorus, and now I need to bind 5 fluorines. There is 1, there is 2, there is 3, then I have number 4, and finally number 5. So there is my skeletal structure. Let us go and count the total number of valence electrons. My phosphorus will bring 5, so that is able to be placed there. And for each one of my fluorines, I'm going to add 7. 7 times 5 is 35, plus 5 is going to be a total of 40 electrons. So now, where do I place those electrons? Well, I have already used 10 of them when it comes to my skeletal structure. So now I have to place 30 electrons around my molecule. Fluorine being the most electronegative, I need to go and place those on my fluorines. So I will go and do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, then finally 26, 28, and 30. I'm officially out of electrons. But notice that my phosphorus is an expanded octet because it already has 5 bonds around the phosphorus, and this is going to be a stable molecule. In this last example, we are now going to look at our xenon tetrafluoride. So what can I do here? Well, we are going to start with our xenon in the middle, and then we will have our fluorines attached to the xenon. Now you're probably looking at xenon and saying, this is a noble gas, how do I expect this to react? Well, there are certain noble gas compounds that react very well with fluorine. This is one of them. So with our xenon, we need to figure out how many electrons we're bringing. Well, we are going to get 8 electrons from our xenon, and we will end up getting 7 electrons from each of the fluorines. 7 times 4 is 28. And then finally, xenon will give us 8 more, and that is going to be a total of 36 electrons. We have used 8 electrons when we are building our skeletal structure, so this means that we are going to have a total of 28 electrons to place. The fluorines will get theirs first, so let us go and put our lone pairs on the fluorines. Remember that lone pairs must be dots, do not draw lines. So now you can see that I have gone and used 24 of my 28 valence electrons. This means that I must place the final 4 electrons on my xenon. So our xenon here is going to have 4 bonding pairs, a pair of electrons going to each one of the fluorines, but then it also has 2 lone pairs. In this video, you have seen the importance of the covalent bonds, not only forming single, double, and triple bonds, but also the Lewis structure in understanding how we can have electron deficient, how we can have odd molecules, how we can have octet compliant rules, and now, as you've seen in this example, the expanded octet. In the next video, you're going to see how we can judge the stability of many of our covalent compounds. Have a great day.